In early fall of 1984, I came here to Oxford University to begin my graduate studies in physics.
Some weeks after, I saw a poster for a lecture by Michael Green. I didn't know who he was, but then again, I really didn't know who anybody was. But the title of the lecture was something like The Theory of Everything, so how could I resist?
This elegant, new version of string theory seemed capable of describing all the building blocks of nature.
Here's how. Inside every grain of sand are billions of tiny atoms.
Every atom is made of smaller bits of matter, electrons orbiting a nucleus made of protons and neutrons, which are made of even smaller bits of matter called quarks. But string theory says this is not the end of the line. It makes the astounding claim that the particles making up everything in the universe are made of even smaller ingredients, tiny, wiggling strands of energy that look like strings. Each of these strings is unimaginably small. In fact, if an atom were enlarged to the size of the solar system, a string would only be as large as a tree. And here's the key idea. Just as different vibrational patterns or frequencies of a single cello string create what we hear as different musical notes, the different ways that strings vibrate give particles their unique properties, such as mass and charge.
For example, the only difference between the particles making up you and me and the particles that transmit gravity and the other forces is the way these tiny strings vibrate.
Composed of an enormous number of these oscillating strings, the universe can be thought of as a grand cosmic symphony. And this elegant idea resolves the conflict between our jittery, unpredictable picture of space on the subatomic scale and our smooth picture of space on the large scale.
And it's the jitteriness of quantum theory versus the gentleness of Einstein's general theory of relativity that makes it so hard to bridge the two, to stitch them together. Now, what string theory does, it comes along and basically calms the jitters of quantum mechanics. It spreads them out by virtue of taking the old idea of a point particle and spreading it out into a string. So the jittery behavior is there, but it's just sufficiently less violent that quantum theory and general relativity stitch together perfectly within this framework.
It's a triumph of mathematics, with nothing but these tiny, vibrating strands of energy. String theorists claim to be fulfilling Einstein's dream of uniting all forces and all matter. But this radical new theory contains a chink in its armor.
No experiment can ever check up what's going on at the distances that are being studied. No observation can relate to these tiny distances or high energies. That is to say, there ain't no experiment that could be done, nor is there any observation that could be made that would say, you guys are wrong. The theory is safe, permanently safe. Is that a theory of physics or a philosophy? I ask you.
People often criticize string theory for saying that it's very far removed from any direct experimental test, and surely it's not really a branch of physics for that reason. And my response to that is simply that they're going to be proved wrong.
Making string theory even harder to prove is that in order to work, the complex equations require something that sounds like it's straight out of science fiction. Extra dimensions of space.
We've always thought for centuries that there was only what we can see. You know, this dimension, that one, and another one. There's only 3 dimensions of space and 1 of time. And People who've said that there are extra dimensions of space have been labeled as, crackpots or people who are bananas. Well, string theory really predicts it.
To be taken seriously, string theorists had to explain how this bizarre prediction could be true. And they claim that the far-out idea of extra dimensions may be more down to earth than you'd think. Let me show you what I mean.